Hi, I'm Jessica, and welcome to today's crash course on missing measurements in solids. We're going to be focusing on area today. This is secondary 2 and secondary 3 material. So for us to review our area, we'll be looking at areas for the formulas of different solids. We're going to also be looking at the area of bases, the lateral area, and the total area of the solids, a little bit of unit conversion, and then finally how to isolate a variable or find a missing measurement. Here we go. To get us started, we should probably just take a quick look at our different formulas. Now, you probably have something that looks like this in your math notes. It's always good to keep this on hand. So it's just a little summary of the different formulas we use in our solids. So we're going to take a look at prisms and cylinders, cubes, pyramids, cones, and spheres. So just remember with prisms and cylinders, the formulas are very similar because both of these solids have two bases. In the case of the prism, we have regular polygons that are going to be making up the bases. And the rectangles we have these rectangles that make up our lateral faces. The distance between the two bases on the prism is what we call the height of the solid. So when you need the height for your area calculations, we're going to be looking at the distance between the two bases. It's the same deal for the cylinder, only this time the cylinder, remember, it has circles as their base, but it's still got the same idea as the height of the cylinder is located between the two circular bases. The cube is, of course, a special kind of prism. Only all of the dimensions are the same on the cube, so it makes it kind of easier to deal with. Finally, we have pyramid and cone. The thing we have to worry about with pyramids and cones, they both are very similar, but there's two heights in pyramids and cones. One is for volume, and that's actually the internal line you see here, the red line, or the pink line, sorry. The pink line that goes from the base to the apex of the pyramid, and also the base to the apex of the cone. That's the height that we use in volume, and it's the height of the overall solid. For area, we're going to worry about that green line that you see on the exterior of the pyramid and on the exterior of the cone. We call that the apothem of the pyramid, or the apothem of the cone. It's also sometimes referred to as the slant height. So you can hear that as well in some of your, or see that in your notes. And I said that these were the last ones, but I'm forgetting the sphere. The sphere, we can't not talk about the sphere. So the sphere is really like the area of four circles combined together into one 3D solid. Here we go. All right, we're ready for example 1. Here we have a regular octagonal prism that has a total area of 640 centimeters squared and a height of 10 centimeters. What is the measure of one of the sides of its base if the apothem of the base measures 60 millimeters? Well, the first thing we've got to do is identify the given measurements. So if I take a look at what the problem says, I'm going to need the apothem, which the problem gives me. Okay, that's my 60 millimeters. So I'm just going to write that right here. Okay, 60 millimeters. I'm also going to need the height. Remember, this is the height of the entire prism. So I'm looking at the pink line here. It's the distance between the two bases. And they give me this in the problem. It's 10 centimeters. So I'm going to write height is 10 centimeters right there. Then I'm going to need the side of the base. But of course, this is the variable that I'm going to have to isolate. Okay, this is actually what I'm going to be looking for. So you'll see later on in the formulas, we use S to denote the side. So I'm just going to put S there. That's what we're looking for. And finally, the total area. So the total area, they gave it to me again. So that's the 640 centimeters squared. I'm going to put that in right here. Oh, it's a little low. So I'll just try that again. That's a little bit better. So 640 centimeters squared. All right. I need to remember to convert the units. So if you take a look over here, my apothem was given to me in millimeters, and my height and my total area were both given to me in centimeters and centimeters squared, respectively. So I'm going to convert everything into centimeters, and to do that, I've just got to remember to take the 60 millimeters and divide that by 10 to give me 6 centimeters. Now I'm ready to determine what formulas I'm going to have to use. And of course, because this is a prism, I'm going to use the prism formula. So the total area for a prism is equal to 2 times the area of the base, 2 times the area of the bases, plus the lateral area. More precisely, my base in this case is a regular octagon. So I'm going to use, instead of the area of the base, I'm going to plug in the formula for a regular polygon here. And then I've got the perimeter of the base, and I'm going to multiply that by height. So now I just need to replace the given values. And of course, we were given the total area, so I'm going to place that over here. That's my 640. And that is equal to, well, 2 is part of the problem anyway, part of my formula anyway. You see the S here. We don't know what that is. That's what we're going to be looking for, but we know that the apothem is 6 centimeters. And then we also know that it's an octagon, so we have 8 sides. The 2 is inherent to the formula, so that doesn't change. When I'm looking at adding that perimeter of the base times the height, again, I don't know the side length, so I still have that as my variable S, and my 8 sides are here, and the height is 10, so it's over here. And I just want to make sure that I'm really clear. Remember, I didn't write it down here, but that's equivalent to 6 centimeters. So remember, this is what we're using in our calculations. That's why I've got the 6 in my formula there. Next, we need to isolate the variable. So of course, we're looking for the S. So the S is going to stay, and we're going to start doing all the math around the S. So if I take 6, I multiply it by 8, divided by 2, it gives me 24. So now I have 2 times 24S. And then I look over here, S times 8 times 10 becomes 8S times 10. And of course, the total area right now is untouched. It's 640. So I keep that untouched on my left-hand side. Another round of math here. And we've got 48 S's plus 80 S's. So when I took 2 times 24, it gave me the 48S. And 8S times 10 gives me 80S. Of course, 48S and 80S are like terms because both of them have the S. So I get to add these together. And they're still just equal to the 640 total area. That hasn't changed. Okay, I haven't touched that left-hand side yet. So I've got to make sure that I reflect that here. When I add my 48S to my 80S, it gives me a total of 128 S's. So now my problem is reading 640 is equal to 128S. So to isolate that variable, I've got to remember, since it's multiplying by 128S, I'm going to have to divide this side by 128 right there. And since I did that over here, I'm going to have to come and divide 640 by 128 also. And when I do that, it gives me my side length of 5 centimeters. So one side of the prism's base measures 5 centimeters. All right, so our second example involves a cylinder. The total area of a cylinder is 1,145.1 decimeters squared. If its diameter is 15 decimeters, what is the measure of its height? So the first thing we're going to do is identify the given measurement. So the diameter is given to us. We know that that is 15 decimeters. So I'm going to write that in right here, 15 decimeters. And although they don't directly give us radius, because we have diameter, if we just divide that by 2, it's going to be giving us the radius. So I'm going to just show that in here. Radius, which is usually a little r, make that just a little bit nicer looking, is going to be 15 divided by 2, which is equal to 7.5 decimeters. There we go. The height, well, the height, we don't really know what the height is. This is, of course, the whole point of the question. It's asking us what is the measure of its height. So this is our unknown. So I'm just going to put, instead of any numbers, I'm going to put in a little h, because you'll see later on that that's what I use in the formula. Finally, we have the total area, which we are also given. So that's the 1,145. That's way too low, so I'm just going to rewrite that. Sorry, guys. Okay. All right. 1,145.1 decimeters squared. Put that in there. All right. Before we go any further, I have a little question for you. What is the formula for the total area of a cylinder? There's more than one possible answer. If you guessed B and D, you're correct. So now it becomes a question of determining which formula to use. So we know that it's the two options that we saw in the previous slide. But you might also realize that the first one, the area total equals 2 times the area of the base plus the area, the lateral area. This is exactly the same as the Prism formula. Okay, so it's pretty generic. We can still use it, but the second one's a little better because it's more specific to the cylinder. You can actually see that the total area is equal to 2 times pi r squared, which remember is the area of a circle, plus the circumference of the circle times the height of the cylinder. So the second one is the one we're going to go forward with because that's the one that's more precise for the cylinder. So we need to replace the given variables. And when we do that, this is what it's going to look like. We have our total area replaced here. So that's the 1,145.1. And of course, that's going to equal to 2 times pi times the radius, which is 7.5. And we got to remember to square the radius. So next, we're going to add that to 2 times pi times the radius, which is 7.5. So 2 times pi times 7.5, all times the height, which of course we don't know. So it stays as just the variable. We're going to start isolating the variable now. So in order to do that, we're going to perform all the calculations that we can, given the information we have. So you'll notice that our 2 times pi times 7.5 squared is going to give us 353.43. It is really important to remember that it's only the 7.5 or the radius that we are squaring here. So sometimes it's a little less confusing if you put it into your calculator first. So 7.5 squared, and then you can multiply that by pi, and then again by 2. Next, we are going to perform 2 times pi times 7.5, and of course we can't do anything with the height because that's the variable we're looking for. So in all, we have 1,145.1 is approximately 353.43 plus 47.12 times h. Because 353.43 and 47.12h are not like terms, we cannot actually do anything else on that right-hand side, okay? We can't add those together. So we're going to have to take away the 353.43 from that right-hand side, and we're going to have to do the same thing over here on the left. And of course, the reason we're doing this is because we've got to get the height alone. So when we subtract it from both sides, we end up with 791.67, equaling approximately 47.12 h. Because we have to isolate the h, and right now it's being multiplied by 47.12, I'm going to divide both sides by 47.12. When I do that, it gives me 16.8 decimeters, which is our height. So that's our height is approximately 16.8 decimeters. Want to remember to just get in a nice little sentence there to summarize that, conclude properly. So we have the height of the cylinder measuring 16.8 decimeters. So for our third example, we're going to be looking at a pyramid. In this situation, we've got at the end of a chain, a jewel is shaped like a regular tetrahedron and made of white gold. We know that its total area is 62.4 millimeters squared, and its bottom measures 5.2 millimeters. What is the length of the chain in centimeters if it measures 75 times the length of one of the sides of the tetrahedron? First, what is a regular tetrahedron? Now be careful here because we want the most precise answer. If you got C, you were right. Here is our tetrahedron. Okay, so first thing we're going to do is identify the given measures. Now, the side is what we're using we're denoting with an S here, and it's actually what we're looking for in the problem. So I'm just going to put my S right here. And then the apothem, that is the green line right here. Sometimes we refer to that as the slant height also. So that is given to us, it's 5.2 millimeters. I'm just going to write my information right here, 5.2 millimeters. And then the total area. Well, that also is given to us in the problem. So if I just scan the problem quickly, it says total area is 62.4 millimeters squared. And so I'm going to put that information right here. 62.4 millimeters squared. Good. All right, next. we've got to determine what formula to use. Now, if you take a look at this, you see that the total area is equal to 4 times base times height divided by 2. And some of you might be thinking, wait a minute, that's not the formula she showed at the beginning when she was talking about pyramids. It showed something different. Well, that's because the tetrahedron is really special and it's made up of 4 triangles. So I'm actually using, and in this case, it's 4 equilateral triangles. So I'm actually just going to use the triangle formula, so the area of a triangle, and multiply that by 4. It's a little more straightforward than going through the pyramid formula. The other thing you might notice is that in this case, because it refers to B and H, and over here, that's not quite the same variables that we used over here. So I just want to point out that when we're talking about the base of the triangle, it's referring to the side. It's the same thing as the side of our tetrahedron. So our side is a B in this case. Got that backwards. I fix that. That is B. Okay. And our H will be the apothem. So if I replace the given variables, then I know that my total area, which was in the problem, is 62.4. And that's going to equal to 4 times B times 5.2 divided by 2. Do the calculations I can, and that works out to being, okay, well, 5.2 divided by 2 gives me 2.6. I still have to multiply it by 4. So right now I have 62.4 is equal to 4 times 2.6b, which ends up as 62.4 equal to 10.4b. To isolate the b, I'm going to actually have to just divide both sides by 10.4. So I'm going to do that right now. And when I do that, it gives me a base of 6 millimeters. That means that my side length for my tetrahedron, which is the base of the triangle, is 6 millimeters. So I'm going to just write that here. Now I want to make sure that I've actually answered the question. And in this case, the question was asking me about the length of the chain. So it told me that it measures 75 times the length of one side of the tetrahedron. So you can see the 75 times the base, which is the length, that one side length of the tetrahedron. So 75 times 6 gives me 450 millimeters. And the question asked me to put that into centimeters. So I'm going to have to take my 450 millimeters, divide it by 10 to give me 45 centimeters. So in all, the length of the chain is 45 centimeters. Okay, so for example 4, we're going to be looking at a birthday hat shaped like a cone. We know that the quantity of cardboard needed to make 50 hats is 19,603.5 centimeters squared. Given that the diameter of the hat is 13 centimeters, what is the measure of its apothem? So the first thing we're going to do is identify the given measurement. So we know from the problem that the diameter of this hat is 13 centimeters. So that's what we're going to write here. And we also know from our previous example that the radius is going to be half of the diameter. So if I take 13 and divide it by 2, so radius is going to be 13 divided by 2, that's going to give us 6.5 centimeters. All right. The apothem, well, the apothem is what we're looking for. So this is going to be, of course, our unknown. We don't know what that is. But you'll remember from our previous examples that apothem is denoted by an A. So I'm going to put A there. The thing is, we have to make 50, we have 50 hats. We know this area of 50 hats, but we don't know the area of one hat. So I'm going to take that 19,603.5 centimeters squared, and I'm going to divide it by 50 to figure out how much cardboard one hat's going to use. And that will give me 392.07 centimeters squared. So the 392.07 centimeters squared represents the area of cardboard required for one birthday hat. But the thing is, we've been talking about total area, we've been talking about area of bases, we've been talking about lateral area, and I want to know if you can really think about what kind of area we're using here. And the thing is, for this, if you look at the context, it's a birthday hat. So there's no base. If there was a base on this birthday hat, we wouldn't be able to get it on our heads. So in this case, we're just looking at the side that one curved side of the cone. So this is what we refer to as the lateral area. Lateral area. All right. So now we have to determine what kind of formula to use. And since we're only looking at the lateral area, we're going to focus on pi times the radius times the apothem. Now remember, we figured out what the lateral area of this cone is because we divided the total area of all of the cones by 50, or all of the hats by 50, and it got us to the 392.07. So of course, that's what we're going to put in place of the lateral area there. Our radius is 6.5 centimeters, and we don't know what the apothem is. Pi, of course, 3.14159, etc. That doesn't change. So when I take, I don't actually have to convert pi, okay? I can actually just take pi and leave it in its symbolic form and say 6.5 pi, divide everything on that side by 6.5 pi, and I can divide everything on this side by 6.5 pi as well. And when I type that into my calculator, it's going to give me the apothem of 19.2 centimeters. So we know that the apothem of our cone, or our birthday hat, is 19.2 centimeters. Okay, so for our fifth example, we're going to look at a tennis ball here, whose surface area is 581.07 centimeters squared. What is the measure of its diameter? So you see our tennis ball right here, and you can see clearly the diameter shown by the red line. First, we're going to do the identification of the given measurements. So diameter, we don't know what that is. So I'm going to leave it as D because that's what the problem uses, and that's what we typically use. Now you'll notice I have a space for radius because actually you may recall that the formulas for sphere require the radius. We, of course, don't know the diameter, so we don't know the radius either here. So we're going to leave this as R. We do know the total area because the problem gives it to us. So this is where I'm going to write the 581.07, and this is centimeters squared. So that's going to go there. All right. So to determine which formula to use, well, there really is only one formula for the sphere. So the total area of the sphere is equal to 4 times pi times the radius squared. When I replace the given variables, I really only have the total area to replace because radius is the only thing we're looking for here. So the radius is going, or the total area is 581.07 is equal to 4 times pi times the radius squared. Now, to isolate the variable, which is the next step that we're going to have to do, so we want to isolate that. We're just going to take both the left and right side and divide them by the 4 pi. And sometimes your calculator is going to need you to put brackets around that to make the multiplication, make sure that you're dividing everything by the 4 multiplied by pi. You might have noticed in the previous example, I didn't put my brackets around it. It actually doesn't matter when we're writing it out. Both of them mean 4 times pi, or in the other case, 6 times pi was the other example. So it does mean it, but it's just a little reminder to you guys that sometimes your calculator likes you to do that in order for the calculation to go well. So we have 46.24 is equal to the radius squared. So to get what one radius is, I'm just going to have to take the square root of both sides here. And that gives me a radius of 6.8 centimeters. So the radius is 6.8 centimeters. Now I know the radius is equal to 6.8 centimeters. That means that the diameter of the tennis ball is going to be 13.6 centimeters. You might be wondering, how did I go from that to 13.6 centimeters? Well, remember, because I calculated the radius, to get the diameter, I had to take the radius, 6.8, and multiply it by 2. So I'm just going to show that to you quickly here in case you had a little trouble following that. Because the actual answer that I was looking for is the 13.6 centimeters, which is the diameter of the entire tennis ball. So that's it for our crash course on finding missing measurements in a solid from area. Please check out our second video, which will be looking at finding missing measurements in solids, but for volume. That's more secondary 3 content, but of course, if you're secondary 2 and want to peek ahead, go right ahead. I really hope this has helped you to understand the topic a little better. And if you'd like a bit more practice, go and check out the exercises that go along with this video.